write at the same memory module as to say. So this is the most restrictive one, that we do not allow them simultaneously to read or write the same memory resources. Less stringent is the concurrent read exclusive write, so that we allow reading of from a memory element to two processors at the same time. We do allow, but writing not. Of course, if we consistently do this classification, then we would also have an exclusive read concurrent write, but in reality that doesn't make sense, right? Because we would ever have a meaningful application that can use this category. Or we have concurrent read and concurrent write. We allow that concurrent writing to memory location. Well, this is the concurrent write is not something which you can do without any harm. So we have to do something with the concurrent write scheme. So either allow common writes if the values are the same, right? But that's kind of trivial, right? If both try to write 5 in a memory location, then either one is okay. Or in arbitrary order, which sometimes is good, but sometimes not, depending on the application. Or we do it through a priority scheme, or we do it in a summation scheme, or generally as an associative operation. Then it doesn't matter in which order we do the operations. So that's if we do allow concurrent write, we have to impose any of these things depending on the application. There are other models than the PRAM model, and one of these models is the BSP model, which stands for bulk synchronous parallel. It was devised by Leslie Valiant in the 1990s, and that works differently. That has as a basis assumption a set of P processors, but not with a shared memory, but with a local memory. And in between is a communication medium that can deliver fixed size messages between any two processors, point to point. Fixed size. So, I mean, the word fixed size is reappearing in these ideal models, right? Because it's essential. And a barrier-style synchronization between the processors. Barrier means what it means in English, that everybody stops at a certain point and goes to the next phase of the operation. So they wait for one another and then go over the barrier together to the next phase. The model parameters are L, which stands for the latency and synchronization costs, G for the computation to communication ratio. That means how it takes care of how fast communication occurs in relation to computation, right? And that's technology dependent. Of course, machine dependent. H is the communication pattern in which each processor sends or receives at most H messages, right? And W is the amount of local work per processor. Now this sounds complicated, but in reality it's not that complicated because it works like this, right? And the computation is divided in what they call super steps in this model. So then each super step we have to calculate the cost of the local computation, right? That is, and the local computation is done without any interference of the other processors. Then we have a barrier. Sorry, not. Then we have a communication phase where each processor sends at most H messages to another processor. And then we have a barrier synchronization. And then we go to the next phase. So it's a kind of looping kind of system. And then the execution time can be calculated by summing over all super steps the amount of local work, the communication computation ratio multiplied by the number of messages. Right? This is the relative factor to weight these terms against each other, plus the latency caused by the super steps. There's a whole school of reasoning trying to derive the complexity of a parallel algorithm against this model. And the good thing about this model is that it takes into account the fact that you have a local memory. So it can also work for distributed memory machines in a sense. So it's more refined than the other PRAM model for these class of machines. Of course, there are some basic assumptions here which may or may not be completely realistic. I mean, the constant size messages, for instance, and these kind of things. But it's still an active field of research. There's a similar model which is called the log-P model, developed a few years later by Kuller and others in 1993, which also is a kind of parallel algorithmic model against which you can judge the efficiency of your parallel algorithm. Now let us try to translate the complexity of these models against real systems, right? So let's have an exclusive read, exclusive write PRAM model, where we have M memory locations in our model, and we have P processors. And if we want to realize equal access to all these memory locations at an equal time, right, then we need the switch between these and these, right, which has complexity M times P, right, because we have M memory locations and we have P processors, so we need a switch. We can arbitrarily select a memory location to a processor connection. There you have NPs, that's okay. But generally, we don't do that, right? We usually do not make all memory locations equally accessible to a processor, but rather organize them in banks. I mean, we need some form of efficiency. So let's suppose that we have B banks, where M is the number of memory locations divided by B, right? Then the M is replaced by B, right? B is smaller, so that reduces our complexity a little bit. But often B is equal or larger than P, right? We have more banks than processors. So that ultimately means that the switch complexity is lower bounded by B squared. And here we have our scalability argument where we started. This is the bad, right? It's not the ugly, but it's the bad, because if we have 1 million processors, we have 1 million squared switch complexity in between. So this is not something we can work with. Right? So with this simple algorithmic model, we immediately see this PRAM model that if we want to build a system to scale to realize this model, we run into efficiency problems. Now let's take the other end. something in between, I think. If we talk about networks, interconnection networks, which are very abstract here as to errors, in reality they take two forms. The first form is what we call a static form, where each processor is connected to a switch and all these switches are connected to one another, and the information is routed from switch to switch, which is connected to a processor to the destination processor. The other one is a dynamic network, where in the network itself we have switches. So not only is a processor connected to a switch, but internally in the network there are also switches to serve as a switching medium between source and destination to the processor. We come into some detail about how this looks like. Let's start with the most simple one, and that is bus-based networks. The scheme is very simple. We have now a number of processors which are connected to, which have their own cache, right, and are connected to shared memory. So all the traffic to the shared memory goes through the this common communication channel. Now, what can we say about these kind of networks? Well, a simple analysis reveals a lot. Suppose that each processor has to access k data words, and that each access costs time t cycle. Right? This is kind of normal, realistic in a system. So if there is no cache in the system, then the execution time of the total system is lower bounded by t cycle times k times the number of processes, because we have to let one another go after one another to the memory. Now this is of course not very scalable, right? Now suppose we have a cache with 50% of the access times local, right? This should improve the system a lot. Then the execution time is lower bounded by 50%, which is in cache, right? Which has this same cycle time, or maybe a little bit faster, but that doesn't change the arguments. Times the other half, which still has to go to the main memory. Now, what can we say if we compare these two? Is this a real better solution or not? Yeah?
It seems to be better because in the half part you don't count the number of processes.
Yes. But it's only a limited view, right? Yeah?
Asymptotically speaking, I don't think it's much better.
Exactly. Asymptotically it's not better. Right? Because it's this term is still dominant if we enlarge k, right, and enlarge p. So asymptotically, and that's just the very strange thing about a cache structure. Algorithmically, it's non-existent. It's only a constant improvement, and still we value it a lot. It's kind of strange, right? Algorithmically, it doesn't improve anything because it's only a constant improvement. But still, it's a dominant thing in most systems. So one wonders why, right? Well, of course, it's noticeable for small-scale systems, but for large-scale systems, it doesn't really make a difference. So we cannot forget about this one, right? It doesn't scale. We can't use it for parallel systems in the end. Now the other end is what we already had, is the crossbar systems where we connect everything to everything. So either P processors to B memory banks or P processors to oneself, right? It doesn't make any difference in the argument. Then we have a switch complexity which is in the order of B times P, which is low bounded by P squared, right? So also that does scale in the algorithmic sense, but it doesn't scale in the hardware sense, right? So we'd be happy to have a system like that to execute our algorithms, but we're not very happy if we want to build it and pay for it, because it doesn't scale. So these are the two ends, right? We have to find something elegantly which is somewhere in the middle to serve our purposes, because we can't use either of them for real parallel systems. Well, the first thing is, why not use a multi-stage network? So we have, for instance, P processors on one end and B memory banks on the other hand. Let's assume they, for the moment, they are the same. So that's, B is N, B is B, or alternatively, B processors connected to P processors. It doesn't make any difference. And have a switching network in between, where in a few stages we can choose the path from one module to the other. Now, would this be an elegant structure? Well, yes. We can do that elegantly by building a stage which has this structure. And this structure is called the perfect shuffle. It's it's coming from a deck of cards where you divide the deck of cards in two halves, right? And you kind of put the cards in between one another, right? And that you see here. And this is a kind of elegant pattern. And so you see what's happening here. And you can also make a mathematical relation between input and output by these two functions. The output j is either 2i or it's 2i plus 1 minus p, depending on the range, right? So that's an elegant structure. The perfect shuffle. And if we do this like this, right? In our 8 systems, we end up with what is called an omega network, and there we have an elegant structure connecting all the source inputs in a few steps to all the destination modules. Now the switch in between is simple. It's either a 4x4 switch. It's either through, right? It connects this point to this point, or it's cross. It connects this point to this point. So it's a very simple switch. Yes.
Every connection, the data flow is serial or parallel?
It's in principle it's parallel, right?
Yeah, but the interconnections are skyward.
Huh?
Like the connections with parallel buses, it's after 8, let's say, processing elements, I think it's gonna skyward.
It's not that bad actually. It's not that bad because there are a number of nice properties here of this network. If we do the analysis, you only need for P processes log P stages, right? And the number of switches per stage is P divided by 2. So the total number of switches you need here is P divided by 2 times log P. So it scales in a certain sense. It's not linear in P. That's really the holy grail in terms of cost. It's not P squared, which is bad, but it's in the middle, right? It's P squared. It's P log P in complexity. So it's a scalable network structure. So this is kind of what we can achieve, right? In terms of network complexity, what is in the middle between the bus structure and the fully connected system. This is a kind of a generic system that in terms of complexity would work. Also, routing is very simple in these networks because depending on the source bit and if we take the binary equivalent of the number of the source and the destination, we can see whether the switch has to put a cross, and that is when the bits are different, or go through, and that's when the bits are equal. So we can, if we have source 1, 0, 1 here, target here 1, 0, 1, 0, 1, 1, we just take the first bit and we say cross, right? We take the second bit, yes, it's cross, and then we take the third one and it's go through. So there is an automatic algorithm to route a message through the network. There's only one small problem. Who can see that problem? So every processor is doing in parallel all these kind of things, right? Yeah.
You only have half the lanes available at any given time. In the sense that the switches, well, they're always in use.
Yeah.
So you can't use both ports at the same time with a given switch.
You cannot always use the switch at the same time because there might be contending paths wanting to use the same switch. That's true. Because if I would have this at the same time, right, I'm having this kind of problems that there are two paths. So now what can we do about that? Sorry?
Just build one register into the switch so that it can be delayed one.
Yes, but then we need a priority scheme, right? And be sure that the buffer is large enough to hold our data. If it's constant data, we can calculate that. But if we don't know the data volume in advance, then we might have a problem. Yeah.
You might be able to simulate one calculation round with multiple real rounds. So
Yes, some kind of time division type of thing that you can also do, yeah. Or you can relay back to the source that the channel is not available, right? Which basically happened in the old telephone system, where you sometimes, I'm not sure anyone encountered this, but when my parents got the telephone, you sometimes picked up the, dialed the number, and then it's whoop, beep, 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 beep. But it didn't always mean that the other side was in conversation. It might just as well be that the intermediate switches didn't have the capacity to route you on. So you just didn't know that. There is even another solution. Pardon?
You can also double each data line so that
Sure, make more capacity available. You can also throw away the packet. Who's using that? The internet, right? Normally you don't build a system like that in the internet way because it's a lot of overhead which kind of in the end it doesn't make the system efficient, right? But in principle, if we talk about first principles, you could do that, right? And then, but of course, then you need an acknowledgement system in return, which would probably dramatically slow down this kind of system. What kind of networks can you build? Well, this is an example of a completely connected network where everybody is connected to everybody, and you see already the complexity here. This is one example. A star network with one computer in the center and a number of satellites in the periphery. A ring or a linear array where you either connect the processors like this or in a ring. These are frequently things. This is an example of a system having a ring. This is the Intel Xeon Phi, one of the newest 50, 60 core machines, which is on the market. Well, on the market, you can buy it. It's probably not appearing in products at the moment. We do some experimentation with this kind of systems at the moment. The Chinese people build it into in their top machine, these kind of nodes into the system. Basically, the processors are scaled down versions of the Intel systems, the Intel architecture chips. And in between is a very fast ring network to be able to communicate, to let the cores communicate to one another and the memory. A 2D mesh, right? This is then a 2D array. If we also make the endpoints connected, then we are talking about a torus connection. There are also chips. This is an example of a 2D mesh in the Tilera chip here. Also a chip you can buy, which uses these two-dimensional. It's handy to make it on a chip, right? This is a bit unhandy, the 2D torus, to do that because you have to make wraparound connections. But if you have to do it not on chip, but in a different way that you can do it, right? With normal wires. Of course, you can also make a 3D mesh, right? And you can make a higher dimensional system. And that you can recursively build up. So you start with one node. It's called Hypercubes. Because you're thinking what's next to a 3D mesh? Well, that's the Hypercube. How does it work? You start with one processor. You'll duplicate it and number the top ones with 0 and the bottom one with 1. So then you have a 1D array, right? You duplicate this one again. Then you get this, and you append a 0 to the old one, and a 1 to the new half, right? Then you have 2D. Then you do it again. You duplicate it. Append the 0 to what you had, and a 1 to the new one. So that's in front is the old one, and in the back is the new one. Right, with the ones here. So now you have 3D, and you can go forward. Right, you can duplicate it again. 2 duplicates, and you connect them, and you get a 4D Hypercube. Right, and you can go on and on and on and on. So why is this an interesting one? Well, it has some very nice properties. It might not be Well, let me take this argument. Yes.
So in the Hypercubes, each level cube should have the same cost for communication in each level, and has different cost for communication with the different levels. From the inner cube and the outer cube. So the inner cube has communicating in the inner cube, you have the same cost communication as nodes communicate in the Hypercube, but between them you get another.
I don't perceive it like that. I perceive it like a single system, and then from any node to any other node there are certain properties.
The maximum distance between each node is something like the diagonal or something like that. I mean.
What do you mean by diagonal?
I mean, in this case it's kind of hard, but in the 3D case it's just the diagonal of the cube and the
it has some nice properties. I'm not sure what you mean by diagonal, but yeah.
Well, for an x-dimensional hypercube,
yeah.
you go from any node to any other node, it's maximum x steps.
Yeah.
So for a three-dimensional hypercube, for a three-dimensional cube, it would be a maximum of 3 steps.
Yes.
And this scales very nicely.
Scales nicely. So it scales with.
Well, in this case, it scales in the number of dimensions.
Yeah. So that's logarithmic against the number of processes, right? Right. So now we get our log, right? So essentially this is what you're saying, right? So if we have a hypercube, which is the number of processes is 2 to the power d, where d is the dimension, then what we have is there are 2 processors in each dimension. The number of connections per processor is log p, so it scales with log p. It's nice, right? Because it doesn't go fast, right? Because making connections to a processor means more bridges, more whatever. And if it's with the log of the number of processors, that's a good property. The maximum distance between any 2 points is log p, which is great, right? It's very fast. And a d-dimensional hypercube can be easily constructed out of 2 d-1 dimensional hypercubes. So it's kind of an ideal system. Whether it's handy to construct is depending on your view. There have been machines constructed with this interconnection scheme, notably some years ago, well, quite some years ago, there was a system on the market which was sold by Intel, which is called the Intel Hypercube. But then the connections were discrete, I mean with wires, and not on a 2D surface, and then things become more complicated, right? With up to 2D, it fits on a surface. But if you go to 3, 4, 5 dimensions, you get all these crossings, and this is difficult to realize on a die. So that kind of structure died a little bit, and there's another reason why it died a little bit, and that we'll come to later. That with the routing schemes, some of these advantages are kind of annihilated, right? So relieved or not so bad anymore. But it's still a reference interconnection structure to which has kind of idealized properties, and therefore it's still important. Of course, we can also have a tree network where and this is an example of a dynamic tree network where the computations, the nodes are in the leaves, and the switches are in the upper half of the tree. Of course, we can also have a system like that where also the intermediate levels are processors. Tree networks also have a form of logarithmic properties, right? Because it only takes a log to go from one end to the other end, right? So they have the kind of a similarity with the hypercube that the distance is logarithmic. The problem is more if a message has to go from one half to the other half, there's some contention here to this kind of part of the system. Where there people found solutions to make the data path on the top much faster than at the leaf nodes, and call them factories. There have been systems that have had this interconnection system in the past based on a factory structure, so people have really built these kind of systems. But it's not that popular anymore. It's been phased out a little bit in modern systems. Let me see whether I will continue with this one or call it a day. For one reason or the other, we need some criteria to be able to evaluate the networks. If we have to choose one, right? One is the evaluation criterion is the diameter. So that's the maximum distance from one point in the network to an arbitrary other point in the network. That's something which is important. The second one is connectivity, which is defined as the minimum number of links to be removed to split the network in two disjoint parts. So how connected is a node? The third one, and that might be an important one or not, depending on your application, is what we call the bisection width. That is the minimum number of links to be removed to split the network in two equal halves. And compare it to your brain, to your two halves, right? How much are they interconnected? Especially with global properties, where you have a lot of communication between one half to the other half, this needs to be a good number. If your application is pretty local, then it's not that important, right? But if your application has a lot of global properties, then the bisection width or bandwidth needs to be a good property. And of course, the last one is cost. And cost is, you can count in many ways. And here we will simply calculate cost as the total number of arcs or wires into the system. Right? So that is something now let's do one example to give you a flavor. So we had diameter, right? We had connectivity. We had bisection. And we had cost. Now, what do you think is the diameter of this network? What? Not too difficult, right? Because at one stroke you're on the other end. So what is the connectivity?
P divided by
P divided by 2.
Q minus 1.
P minus 1.
P minus 1. P minus 1. Right? So you just have to cut one node. And it has P minus, because it has to connect to every other process, it's P minus 1. Now the bisection. That's more difficult to see, right? say cut it in into halves. B?
P square?
P divided by 4,
B divided by 4.
so you have to remove whatever you know.
Yeah.
You can remove half of that,
Yeah, half of the, yeah.
so it's basically
I think there's B divided by 4 in there, yeah. B squared divided by 4. Right? So the divided by 4 was okay, but then for every processor, right? So this B squared by 4. And then the cost,
P square? Oh no. P minus 1 square?
so each processor has P minus 1 connections.
Yeah.
So that's P times P minus 1, but you count double, right? So you have to divide it by 2.
Double.
Yeah. Right?
Count double.
So then, so this is not very nice, the last two, right? This P squared properties. So with a little bit of thinking, you can kind of derive the basic numbers for these according to these 4 criteria.
I got the impression that you want the bisection to be as high as possible.
Yes, but it's
Within
high.
reason, of course.
It's high here.
Yeah, but why is that then a negative property, or not so nice property?
Oh, this one is nice. No, it's the cost is not a nice property. No, this one is extremely nice. So you pay a lot, but you get something nice, right? Okay, see you next week.